Okay, so in the last video, we used the Crank-Nicholson. We made all these matrices. We showed how something would propagate through an object from 50 to 80 degrees, how it would propagate through the center. It was great. We used all these different R values. We made plots. We found that unlike part A, when we used von Neumann, when we use the Crank-Nicholson, we can use essentially any R value up to some pretty large numbers. But in part A, we can only use an R value up to 0.5. So we're going to show why the Crank-Nicholson scheme is stable for all R values and not just the specific ones. So you can see here we've rewritten the equation that we used in the last video, and we want to see how these things relate to each other. So minus R Tj plus 1 n plus 1 is how does that relate to Rtj plus 1 n? So how do these two things relate? So we know that in our original video, in video A, we use Euler's identity. We use some of those terms. So we can do that again here. And we can remember that our identity is up here, so it might be kind of hard to see that we want to be shifting these terms so they're on the same length. So anywhere we see that I plus 1, we can use this identity, and then we see that I minus 1, we can use this identity. So let's go ahead and rewrite what we've got going on here. So we're going to have Tj to the n plus 1 like that. We can factor that out, and then we're going to go ahead and add all of our identities. So we'll have minus R e I k delta x plus 1 plus 2r minus R e minus I k delta x, and that's going to equal T j to the n times R times e I k delta x plus 1 minus 2r, and then finally plus R e minus I k delta x. Okay, so here's our equation that relates these two things. Sorry, the glare is pretty bad, but here's our equation that relates those two things. Okay, and we can remember that Euler's identity can be written like this. So e to the ix is equal to cos x plus I sine x. So we can go ahead and apply that to our terms. So we can say that any e to the I k delta x is going to be equal to cos k delta x, like that. And then any sine is going to be plus I sine k delta x. We can do the same for negatives, so e to the minus I k delta x is equal to cos k delta x. We carry that minus sign with us for that minus I, so minus I sine k delta x. If we go ahead and add these two things together here, sine k delta x cancels, minus I sine k delta x equals, and that it's going to equal 2 cos k delta x. So we can see that anytime we add those two things, we're going to get that 2 cos k delta x. So now we can actually rewrite, I'm going to choose a new color, we're going to do yellow. So now we can rewrite our previous equations. So we have let me make that a little bit thicker, sorry. So then we can say we have Tj n plus 1. We still have our 1 plus 2r, but now we have, I guess we're subtracting. We can factor out a negative here. We can say that we have minus r, and then we're adding, so then we can say that we have that 2 cos k delta x, like this. And we can set that equal to Tj J n. We're still going to have our 1 minus 2r, but then we'll have plus r 2 cos k delta x, like this. So now we've used Euler's identity to go ahead and move this problem along a little farther. And now we just have one final step left. We got to do a little bit of algebra, so we're just going to divide everything on this side over. And so when we do that, we'll get that tjn plus 1 is equal to tjn times, we'll pull the constant r values out, so we'll have 1 minus 2r over 1 plus 2r, and that will be, we'll have 2r cos k delta x over minus 2 cos 2r cos k delta x, like so. And we know that cosine ranges between minus 1 and 1. It can never be anything other than these values. So, yeah, sorry about that. So we can see that we have cosine can never be the absolute value can never be greater than 1. So let's just say we, I don't know, have our cos k delta x is equal to minus 1. Well then, okay, that's great. So then we'll have just 2 over 2, and that's equal to 1. And so then our value is 1 minus 2r over 1 plus 2r, and that'll just be times 1. And I think, let me check on that. Yes, we have the right idea. So basically our relationship is 1 minus 2r over 1 plus 2r. That's our final relationship. And for any value you plug in of r, this value can never be less than negative 1 or more than 1. So we can plug in, I don't know, if we plug in 5, we'll have 1 minus 10 over 1 plus 10. We'll get 9 over 11. Even if you plug in 100, you'll get 199 over 201. So for any r that we plug in, it cannot become unstable. That's why using the Crank-Nicholson scheme, any value is stable for r. Some are more stable, but any r value is stable using this. That's my proof. Here are the equations. Thank you for watching.